Hello everyone. Today, this is soft-valid binary search tree. So given a binary search tree, we have to check whether or not it's a binary search tree, right? So the rule is that anything we use the root as perspective. Anything to the left should less than the root. Okay. Anything to the right should be bigger than the root. And also is applicable for the subtree. So we have to, it means that as long as we go left, it means that we should less than our parents, right? So as long as we go left, we have max upper bound, right? 25. And we don't care about minimum. So we just inherit from its parent. But this parent is root, so we don't have anything to inherit. And go left. Go left means upper bound. So we just update the upper bound and inherit the lower bound. Inherit the lower bound from its parent. Its parent is nothing. To the right means that we have to update the lower bound because we have to follow that to the right we have to greater than its parent. So after update the lower bound, inherit from the upper bound. So it's 25 from its parent, right? From its parent, and its parent is max 25. Why? Because to the border perspective, this 20 is to the left of this node, right? So this node have to follow the first rule that we have less than the node, right? So let's see. Let's continue to the left. So as long as to the left, we have to update the upper bound, max 20, and inherit the lower bound, mean 15. Okay, so same here. To the right, you have to bigger, so update the lower bound, inherit the upper bound, update the lower bound from its parent, okay, and inherit the upper bound, nothing. To the left, update the upper bound, inherit the lower bound. Lower bound is this one, mean 25. Because this node is also to the right of this its root, right? Okay, here. In here, let's draw it here. Left means update the upper bound, become 28, and inherit the lower bound. Lower bound is this node, 25. Okay, so we just do it recursively, and we were able to solve this question. So let's see the code so that you will have a better understanding. Right. Copy the code here. Previous. This node, no. Okay. So let's create a helper function. Yeah. It's also called is valid. This code is valid. Okay. It's root. Tree node. Root. It's the current node. It's the current node. Current node. And upper bound is max, or lower bound is mean. Okay. And also return bool. So it's valid or not. So check the edge cases. If root is nil. Nil's, I'm not sure nil is a value or not, but let me return true first. And then let's do the check it for the root. For 25, we don't need to check anything. So it's valid, put root here, and the max is new. It's nothing to check. For 25, it's nothing to check. New. Just return it. And here's the something we have to check. So if cur, yeah, we have to return true. I would say if cur is new, we just return true, because maybe in here nothing to check, so we have to return true here. If we go from here to the empty node, and if we have max node, max not equal to new, means that maybe we are here, right? So we have to check our upper bound. So if max not equal to new, we have to check whether or not current value is bigger than our max value. And then just return false. Another one is the lower bound, so mean. This. So mean is lower bound, right? So we have to bigger. So if we are smaller than our lower bound, means it's false. And then we have to check left and right, right? So start from 25 and it go left, so it's left, right? So we just put left here, and we also have to check the right part, right? So put right here. And to the right, right? I have mentioned that to the right, to the left, up. Use the parents as max upper bound. So we just put the use the current node, right? Left. So its parent is the current node as max, and inherent the mean bound, lower bound. So mean here. And to the right means that its parent is the lower bound, right? So its current is the lower bound, and the max just inherent. So just put max here. And then we don't have a root, yes. Just put current here. And yeah, that's it. And the time complexity for this algorithm, just we loop through all the nodes, right? So space complexity, because we don't use any space. So space is O1. Let's see. Okay. Submit. Yeah, so that's it. Thank you for watching.